All right, I think we can start. Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Lars Lindemann, who is an assistant professor at the Department of Computer Science at the University of Southern California, and there he leads the Safe Autonomy and Intelligent Distributed Systems Lab. So something about Lars: he received his PhD in electrical engineering from KTH, Royal Institute of Technology, back in 2020. Then he moved to warmer weather, or similar weather, let's say, where he was a postdoctoral fellow for a while at the University of Pennsylvania, and now is definitely in a better weather at University of Southern California. So his research interests include the systems and control theory, formal methods, and safety in autonomous systems. And for his work, he received a number of awards that you can see in the bio. And today he's going to talk about safe control of learning-enabled autonomous systems. This is clearly a very important topic and a very interesting one for this seminar series. And therefore, I'm very excited to hear more about it. And I give you the stage, Lars. Go ahead.
Yeah, thank you so much, Yola, for the introduction and also the invitation to give a presentation here today, which, like you said, is about safe control of learning-enabled autonomous systems. In particular, I divided my talk into two parts. In the first part of the talk, I'm going to talk about how we can learn safe control laws from expert demonstrations. And in the second part of the talk, I will be presenting recent results on how we can use statistical tools for safe planning in dynamic environments. First off, what are autonomous systems? Autonomous systems are engineered systems that operate in complex and open-ended environments. They perceive the environment, they reason and learn from data, and they act in order to achieve a wide variety of tasks to improve society and to improve life for everybody. Autonomous systems research particularly promises to enable many future technologies, such as in the automotive industry, in manufacturing, healthcare, and aerospace, but also in robotics applications, agriculture, connected cities, and automated services. And all of this certainly highlights the importance and the potential impact that autonomous systems research can have. Over the past years, the wide availability of data coupled with the computational advances in machine learning and AI has really accelerated the progress that we have made to build these autonomous systems. And I've shown three videos over here where you can see autonomous systems really perform highly challenging tasks with these. We see Boston Dynamics robots, we see Tesla cars, probably you've all seen those, but also a drone fleet from the Kumar lab that do their challenging tasks here. From these demonstrations, one could certainly claim that, yes, autonomous systems are a reality. However, the question that I would now like to ask is, do we really have all the theories and tools at hand to build autonomous systems that are also safe? And I would argue that the answer to this question is no, simply because at the same time we have observed a lot of failed demonstrations. We have seen Boston Dynamics robots failing. We've seen Tesla cars crashing, even endangering human lives, unfortunately, in some cases, even killing humans. And we have seen drone fleets collapsing. Even more so, it turns out that learning-enabled systems are fragile. Going back a few years in time to 2015, particularly, there was a big hype about self-driving cars, which there's still a big hype. But as of now, we really don't have fully autonomous cars. Even worse, it turns out that the industry has reset their expectations to only level 4 autonomy, meaning that we will only be achieving full autonomy in certain more controlled environments. Due to these challenges, researchers, for instance here from MIT, have focused on more solvable problems such as autonomous boats. So what are the problems and challenges that we're facing? One problem seems that the way that we train our AI is fundamentally flawed. We train and tweak our algorithms to lab-like environments that then fail in real settings and under real circumstances. One famous example that illustrates the fragility of learning-enabled systems is this panda example, where we have an image that displays a panda and a machine learning algorithm that classifies the image as a panda. But once we put some small noise on top of the picture, the resulting picture really looks the same to the human eye, but suddenly the algorithm classifies it as a given. So the question then becomes, how can we make autonomous systems safe? Can you still see me or hear me?
I just see a black slide, but I hear you.
Somehow my presentation stopped. Now
Okay,
it's
we
back
see
on.
this, we
Sorry,
see
this
that,
is
yeah.
okay. Let me repeat. So I was just saying the question then becomes, how can we make autonomous systems safe? But also, what are the fundamental limitations that we're facing, and what are the safety and performance guarantees that we can provide? Okay. So today I'm going to talk about two topics in this broad area. Like I said, first about learning safe control laws from expert demonstrations, and this falls under the umbrella of data-driven control, which is the first research thrust that I'm addressing in my group. And in the second part, I'm going to talk about safe planning in dynamic environments using a statistical tool that's called conformal prediction, and this falls under the umbrella of risk-aware autonomy. In my group, I'm also addressing questions on distributed autonomy, so multi-agent systems. I'm working on formal methods and control. Actually, that's a large part what I did during my PhD at KDH. And more recently, I became interested in human-centered AI. So how can we quantify uncertainty of humans, and how can we do safe decision-making with humans in the loop? Okay, so let's jump into the first part of the talk, which is about learning safe control laws. In general, we can say that the system is safe if its behavior is safe. Okay, I would like to use a bit more of a control-ish language now, though, and say that a system is safe if we can control it to stay within a safe declared set calligraphic C. So if we have a robot over here and the safe set, which is the blue region, then the robot is safe simply if we can control it to stay within the set. This, of course, is a well-defined and well-studied problem. There are many existing techniques, one being simply handcrafting safe control laws, but this is typically limited to simple systems and often doesn't provide any safety guarantees, for instance, if we can't find a suitable Lyapunov functions or something alike. There's a large body of work on sum of squares programming, Hamilton-Jacobi-Bellman reachability analysis, and discrete program synthesis, which comes more from the computer science domain. But all of these three techniques share the similarity that they have scalability issues, and that in order to use these techniques, approximations are needed. And then largely used is also model predictive control. However, there one may require potentially heavy online computation, which may be restrictive. So in summary, we can say that finding safe control laws is challenging. And the question that we were asking ourselves is, can we leverage data and use machine learning techniques instead to do so? Now, looking at these three examples that I've shown on this slide, one may say that the systems that are displayed are really different, especially in terms of their dynamics. However, I would now like to argue that they share some key properties that lets us reason about their safety roughly in the same way. First of all, these examples are really data-rich in the sense that it's easy to get access to data that exhibits safe system behavior. For instance, thinking about autonomous driving, we have a lot of safe driving behavior at hand, right? Second, the dynamics of these systems are highly complex. They are nonlinear and often hybrid, meaning that the systems are described by continuous motion as well as discrete events. For instance, here when the bipedal robot, when the leg hits the ground, that's a discrete event. But on the other hand, these dynamics are really well understood, and we have good tools to model our systems accurately. And what we want to do in this part of the talk, we want to use the availability of data as well as the availability of good models to learn safe control laws. Let me give you an overview of the framework. First of all, let us assume that we know the dynamics. We will relax this later to unknown dynamics and also hybrid dynamics, but let's for now assume that the system is described by this ordinary differential equation where f and g, the functions f and g are known. Second, we assume that we have a set of expert trajectories, which are really these spaghetti trajectories that are indicated here, that are safe in the sense that they evolve within a safe set, which is this red box. What we then do is we feed these two things, the known dynamics and the set of expert trajectories, into a constrained optimization problem that I'll explain in the remainder, with a goal to learn a safe control problem. In fact, what we do is we learn a function that approximates the operating region of the experts, here indicated by this blue ring, and that will give us a safe control law for free. Our contributions here is an algorithm with formal safety guarantees. We show how we can handle perception uncertainty, and we can do so even for unknown and potentially hybrid systems. From now on, it's going to be a bit more technical. I'm going to introduce the machinery that we use to enforce safety, which are control barrier functions. So again, assume this ordinary differential equation and assume that we're given a function h that acts on the state of the system, for instance, the position, velocity, and so on. And let the safe set now be defined via this function h as the zero super level set of the function h. So each point h for which each point x for which h is non-negative will be considered safe. Now, intuitively, what do we need to do to ensure safety of our robot? Well, simply, whenever we're on the boundary of the safe set, we need to make sure that we have a control input such that the time derivative h dot is non-negative. And by the definition of the safe set, it will then guarantee safety. This intuition can be formalized by the notion of a control barrier function. And we say that the function h is a control barrier function if we can pick a control input such that h dot is greater or equal than minus alpha, which is an extended class K function. So a strictly increasing function that is 0 at 0 that is composed with our h. This 0 at 0 property of the extended class K function in particular guarantees that we recover this condition because on the boundary, our function is h0 so that the right-hand side on the boundary becomes 0. Okay. Now, for the particular dynamics that we're looking at that are input affine in U, this h dot expression simply evaluates to the gradient times the dynamics. The reason why I'm showing this equation is simply that once we have shown that we have a valid control barrier function, this equation, this constraint here is linear in U so that we can get a safe control law easily. Just one piece of terminology, I'll refer to this constraint in the reminder as the CDF constraint. And like I said, once we have shown that we have a valid control barrier function, life is great and we have a safety factor, okay? However, the difficulty and bottleneck is really that it's hard to construct these control barrier functions and we would like to learn them from data here. So let's get back to our spaghetti trajectories that I talked about before. And let's pick a data point xi, okay? Like one data point from these spaghetti trajectories. And let's put a ball of size epsilon around this data point, which is indicated by this orange ball over here. In fact, let us now do this for every data point in our data set, and let's take the union over these so that we get this orange donut that is shown over here that we label as the set of safe states. What we need additionally is a set of unsafe states. So what we do using computational techniques is we sample unsafe states at the boundary of our safe set, here indicated by these gray rings. And now we have defined safe and unsafe set, and we're ready to write down our optimization problem. First, some piece of notation. We define our CBF constraint by this function Q. And then we have this optimization problem that I'll walk you through slowly right now. Like I said, we want to find a function H that comes from a certain function class, calligraphic H. This could, for instance, be the class of neural networks. And we would like to, on top, minimize the complexity of our function. Now, we have three types of constraints that are important here. The first type of constraint acts on the unsafe data points in this gray region. And here we would like to push the function h to be negative, okay? We would, in fact, like h to be strictly negative and upper bounded by minus gamma, where gamma is a positive robustness slack. On the other hand, for all safe data points in the orange region, we would like to push h to be positive. In fact, we would like to push h to be strictly positive and lower bounded by gamma. And by these two constraints, we enforce that the zero level set of the function h is somewhere in between the boundary of the gray and the orange region, so between the safe and unsafe set. On top of that, we enforce the CBF constraint by using the expert action that we also assume to have recorded. And we again enforce these CBF constraint with a robustness slack of gamma. Okay? And we do this for all data points in the safe set. Now, for a moment, let us assume that we can solve this optimization program and that we can find a feasible solution H, okay? Then we show that this H is a safe control barrier function if three conditions hold. First, if the data points are dense enough, if the functions H and Q are smooth enough, and if the robustness slacks gamma are big enough. So simply what we have to show is that our epsilon that defines these small balls that I showed in the beginning are upper bounded by the robustness slack over the Lipschitz constant of the functions H and Q. How do we solve this optimization problem? Well, for general function classes calligraphic H, this is a nonlinear optimization problem, a non-convex optimization problem. However, if we parameterize H in a certain way, we can obtain a convex program. For instance, if we parameterize H in the following way, we choose some nonlinear basis functions, for instance, Fourier features, and we linearly parameterize it with a decision variable that I denote here by theta, then we can show that we have a convex program that we can solve reliably and efficiently. However, if we would like to resort to neural networks to use their expressivity, then in general, we have a non-convex program. And what we do is, in practice, instead of solving this nonlinear constraint optimization problem, we solve an unconstrained optimization problem. And we do so by bringing the constraints that we have here into a constraint function using this max reformulation. So you will note that when this max here is 0, the constraints, the original constraints are satisfied, while adding it with a Lagrange multiplier that we optimize over, that we maximize over. And we do this for all 3 types of constraints. Okay. Let me show you first a toy example. It's a 2D example of a feedback linearizable system. Our goal here is to track a reference trajectory while avoiding the red regions for safety purposes. First, we need to collect expert demonstrations. So what we did is we used an MPC to track a reference, and then we designed an analytic control barrier function to enforce safety. Okay. We collected safe data that you can see denoted here in green, and unsafe data shown in red, and we have some buffer states in between. Okay. From this data, we learned a control barrier function, a function that is parameterized in this convex way that I just talked about by using 200 random Fourier features. And you can see the level sets shown over here. Basically, the ring in the middle, the ring over here indicates the safe region, which you can also see in the 2D plot. Now, what we need to do is we need to check these conditions that I talked about of data density, robustness, and smoothness. And we need to do so for all 3 types of constraints. And what we see here is for the safety constraint and the unsafe constraint, this holds, as well as for the CBF constraint. So we have, in fact, learned a valid control barrier function. So far, I've assumed that we know the dynamics of the system exactly, and I promised that I would relax this assumption. That's what we're doing now. Here, in general, we can note that the functions f and g may not be known. Okay. However, what we may have is we may have accurate models f hat and g hat, along with error bounds delta f and delta g, that bound the point-wise difference between the system and our model. Okay. And what we can then do is we can replace our CBF constraint that I recall here for completeness by a robustified CBF constraint. So what we do is we just replace in this constraint our f by f hat. We keep this extended class K function as it is, and we add a robustness term that looks as follows, that includes the delta f and delta g that quantifies the error that our models may have. Okay. And then in our learning problem, we simply use this robustified CBF constraint. We have implemented this in an autonomous driving simulator, Carla. On the left-hand side, you can see an expert controller. In this case, this is a PID controller, but it could really be a human operator from which we unroll trajectory data and learn a CBF that you can see on the right-hand side. And not surprisingly, you see that the learned CBF controller closely imitates the safety behavior of the expert controller, and by that, our algorithm stays safe. Now, so far, I've also assumed that we know the state of the system X exactly. However, this may not always be the case. And we focus on scenarios where we have high-dimensional sensor measurements available. For instance, dashboard camera images, okay? Now, for such high-dimensional sensors, the sensor map P is unknown, but it's a reasonable assumption to assume that there exists a hypothetical inverse that would recover the state. This inverse is, of course, unknown. In practice, this may, for instance, be from a dashboard camera images, we may estimate or be able to recover the state of the car, the position, for instance. Under this assumption, we assume that we have an estimator P hat available that recovers our state X hat. And we again assume that our state X and the estimate X hat are bounded by some delta P. Okay, so we assume that we have a bounded state estimation error. And we're playing the same game as before. We have our original CBF constraint, and we use a robustified version of that, simply by first replacing the unknown state X by our state estimates, and by adding a robustness slack, a robustness term again, that consists of Lipschitz constants of the functions f, g, and h, as well as our delta p that quantifies the estimation error. We implemented this in Carla again. We used dashboard camera images. We resized them to be able to deal with larger images, so simply downsizing them. And we trained perception map, which is a ResNet 18 neural network here. And from there, we trained a perceptual control barrier function that you can see here keeps the car safe. The control input is a bit more jerky, but this is probably because we didn't really fine tune it in the end. Lastly, I would like to talk about hybrid system. I'm not going to show you the theoretical result. I would just like to show you an experiment that we did with a passive walker, this small walker that is walking down an inclined ramp. It has actuation in the hip and in the ankle joint. However, if we don't actuate the system, we will see that the walker will just fall down after a couple of steps. So what we did was, from the literature, we used an energy-based controller to collect expert trajectories. And we trained a 2-hidden-layer fully connected neural network. Okay, and the result you can see here, the walker walks down safely the inclined ramp, and the correcting control actions are indicated by these green arrows in the hip and the ankle. I would also like to show this figure here, which is a bit more of an empirical evaluation. On the right-hand side, you see the energy-based controller. On the left-hand side, you see the control barrier function controller that we learned. Each dot here indicates an initial condition of the system. We have a 4-dimensional system. What we did is we fixed the position and velocity of the left leg, and we varied the position and velocity of the right leg, which is shown here in this 2D plot. If this dot is blue, it means that the trajectory unrolled from this initial condition was safe in the sense that more than 10 steps were walked. If it's red, it means that less than 10 steps were walked. Okay. Interestingly, what we see is the safe region indicated by this black line over here approximates the safety or emulates the safety behavior of the expert. What is also interesting to notice that in some regions of the state space, especially here, the CBF controller is doing better than the expert controller, which has a lot of unsafe walks there. And we suspect that this is because we induce a lot of robustness in the learning by these robustness flags gamma, if you recall, so that at least in this example, our CBF controller is even doing better than the expert. By this, I would like to conclude the first part of my talk and jump into the second part. While in the first part of the talk, we have focused on learning safe control laws by largely neglecting the environment, I would now like to focus on autonomous systems that really have to operate in unknown and in dynamic environments. My ultimate goal here is to design verifiable and uncertainty-informed motion planning algorithms for systems that operate in dynamic environments. Let us first take a step back, though, and let us look at a modern autonomy stack. This autonomy stack typically consists of a system, right? In this case, this would be a car, as well as the environment. And the environment may be, like I said, unknown and dynamic. On top of that, we have sensors. We may have camera, LiDAR, and radar. And we have perception algorithms that map our sensor measurements into state estimates, so of states that are of interest to us for our planning and control module. Now, in such a modern autonomy stack, especially the perception module has complex layers of neural networks for semantic labeling of agents in the environment, as well as for their prediction, for predicting their future motion. Okay. Similarly, in the planning and controls module, we may have neural networks. For instance, as I introduced in the first part of the talk, we may have learned CBFs. The question that I would now like to ask is the following. How do we formally reason about safety of these high-dimensional systems? And by high-dimensional, I would really like to emphasize that once we have perception algorithms, for instance, the ResNet 18, we may have, really hundreds or thousands of neurons that we have in this autonomy loop. So how do we reason about the safety? There are existing techniques, for instance, satisfiable modular theory solvers or mixed integer linear programming techniques that give exact solution to this problem, or hybrid systems reachability tools. However, it is known that these techniques simply do not scale, especially not to the size of the, or to the dimensionality that these systems may have. On the other hand, there are more scalable techniques, convex formulations like semi-definite programs or linear programming relaxations, or even compositional approaches. However, it turns out that these approaches are overly conservative and also not usable in practice. To make matters worse, there may be a lot of randomness in the system. We may have disturbances acting on the car, noise acting on the sensors, and more importantly, we may have randomness in the environment as, for instance, unknown intentions. So what I would like to do is I would like to navigate this trade-off between scalability and conservatism and be able to deal with the randomness that enters this closed loop system. And the question that we were asking ourselves is, can we use statistical tools instead to formally reason about safety for autonomous systems? I would now like to pick a particular autonomy problem, which is the safe planning problem in dynamic environments. In this problem, we would like for an ego agent, for an ego vehicle, let's say, find a path that avoids dynamic agents in the environment with a probability of 1 minus delta. Okay. So if we have the car over here, we would like to plan a path that avoids other cars and other pedestrians in the environment with a probability of at least 1 minus delta. What are the challenges here? Like I said, we have complex perception and prediction algorithms in the loop. And it's difficult to quantify uncertainty of these algorithms and bring them into play. Now, there exists a lot of planning techniques that I want to mention. Vanilla motion planner, for instance, graph-based methods. However, these typically ignore the dynamics of the agents. There are reactive methods, for instance, navigation functions. However, they don't use predictions of how agents may evolve in the future and are hence conservative. And by using predictions, we can really improve the safety of the system. On top of that, these methods often assume simple dynamics. And more recently, there are predictive methods, so really that use predictions of the environment in interactive and non-interactive ways, and they solve the problems in belief space. However, to do so, often approximate solutions are found, or simplifying assumptions are made. And by simplifying assumptions, I mean that often linear dynamics are assumed, or for instance, Gaussian noise is assumed. We don't want to do this, and we want to quantify uncertainty of prediction algorithms, of learning-enabled prediction algorithms, and use these downstream for safe planning in such scenarios. I would like to motivate our approach by 4 observations. Looking at these 3 pictures over here, we can observe that the robot dynamics, again, as in the first part of the talk, are well understood, and the robots can be modeled accurately. So we can model cars, we can model mobile robots with sufficient accuracy. However, when it comes to dynamic agents, such as pedestrians, these are highly uncertain, and in general, they're super hard to model. Okay. What we, however, have is we're living again in a data-rich world, and we have large data sets that describe the motion of dynamic agents. And on top of that, we have really powerful motion predictors. We have accurate learning-enabled motion predictors that we can use together with these data sets. Okay. So what we want to do now is we want to use these 3 things. So the models of our robot, the data sets describing motions of dynamic agents, as well as our motion predictors. And on top of that, we want to use statistical tools, such as conformal prediction in this case, to quantify uncertainty of our predictors and to use these downstream for uncertainty-aware motion planning. Let me give you an overview of the framework that we propose. We start with assuming that we have an offline trajectory data set. So in this case, assume that we have observed a lot of trajectory data from pedestrians that walk at an intersection. Okay. Now, during runtime of the system, we make observations. So at time t, during runtime, we say that we have observed how this pedestrian that is illustrated here walks or has been walking over the past 5 seconds. And we indicate or denote this by the variable y. So y of t means position of the pedestrian at time t. What we then do is we use a trajectory predictor, for instance, a recurrent neural network, to predict the future motion of this pedestrian. And we denote these predictions by y hat. Now, having these predictions is good, but we don't really know what is the uncertainty of our trajectory predictor. The trajectory predictor could be really good, or it could be really bad, right? So what we would like to have is we would like to have a tool that tells us how good are our predictions really. And this is exactly what conformal prediction is giving us. Basically, conformal prediction is using the offline trajectory data that we have available to quantify uncertainty of our predictions. So what we get is these blue prediction regions that indicate that our pedestrian will really be contained within this prediction regions with a probability of 1 minus delta. Well, that delta is a user-defined failure probability. So we can really basically get a measure of uncertainty for our predictions. And what we then do is we use these predictions along with the prediction regions and the robot dynamics to design a model predictive controller that guarantees probabilistic safety. And by that, I mean that we have a safety constraint C that acts on the robot state X as well as on the pedestrian position Y. And we can ensure that the safety constraint here holds with a probability of 1 minus delta. Our contributions here are really a computationally lightweight and simple algorithm that comes along with probabilistic safety guarantees. And we show also that we can deal with distribution shifts. And I'll talk a bit more about this towards the end of the talk. First of all, though, I would like to give you an introduction to conformal prediction. So I labeled this as conformal prediction in a nutshell. As I said, conformal prediction is a tool for uncertainty quantification. And the cool thing about it is that it works under minimal assumptions. And by that, I mean that it's distribution free. So let us assume we have a supervised learning setup where we have inputs X and output labels Y that are drawn from a distribution D. And we don't need to make any assumptions on D. It could be a Gaussian distribution, but it could be any other funky distribution. We also don't need to make any assumptions on the predictor that we're using. So assume that you have a predictor mu that maps an input to an output label, to an estimate. Then we don't need to assume anything about mu. It could be any neural network, really. However, what we need to assume is that we have availability of validation data. So of input, output data points that we have on top of our training set, for instance, that we use to train our neural network. The goal in conformal prediction is then to fix a failure probability delta. And we would like to obtain a prediction region C such that the true but unknown label during runtime is contained within this prediction region with a probability of at least 1 minus delta. Just to illustrate this, assume that we're given 3 images and a prediction algorithm, okay? So for the left image over here, which is really clean and easy to predict, then the prediction region C may simply contain 1 label. However, if the image gets more difficult to classify for our predictor, then this set C may only contain 4 labels, may contain 4 labels. So a larger set of labels indicating that there's uncertainty, right? And then for the third image, which is even more difficult to classify, it may contain 6 images. I would now like to talk a bit about the underlying technical machinery. So I'll show you what conformal prediction is based on, which is a quanti-lemma. I'm going to show you the technical result and walk you through it briefly. What we assume is that we have k+1 IID random variables, okay? And these IID random variables, they're typically referred to as the non-conformity score. You can just think about it as the prediction error. Our goal now is to find a prediction region for R0 based on the values of R1 to Rk, okay? And what we can show is that with a probability of 1 minus delta, it holds that R0 is bounded by the 1 minus delta quantile over the empirical distribution of R1 to Rk and infinity at. Let me illustrate this. Let's plot the histogram of R1 to Rk here in green. So the nonconformity scores are on the x-axis and the frequency by which the values occur from Rk to R1 to Rk are plotted on the y-axis. The 1 minus delta quantile is, or could be, this black line. By adding infinity over here, we shift the quantile a little to the right, here indicated in pink, and we account for the fact that we only have finite data. Now, one may ask the question, how can we calculate the quantile? It's really simple. We simply take the k+1 times 1 minus delta's smallest nonconformity value. This operator here is simply the ceiling operator. For the specific choice that we looked at so far for supervised learning and the specific choice where we simply consider this error as our nonconformity score, the prediction region is simply centered at our prediction, and the size of the region is indicated by this 1 minus delta quantile. And the beauty of this is really that using conformal prediction, if you have a bad predictor, the prediction regions will be large. If you have a good predictor, the prediction regions will be small. So you simply quantify uncertainty. Now, let's get back to our problem for planning in dynamic environments. And let us assume that we have pedestrians that walk according to a random trajectory, okay? And we denote this by y0, so the position of a pedestrian at time 0, y1 position at time 1, and so on and so forth, okay? Now, during runtime, what we do is we observe observations from our position at time 0 to the position at time t, and we obtain predictions for the future. So for t, capital T seconds, steps ahead. And we can do so, for instance, like I said, with recurrent neural networks. And in our case, we used long short-term memory networks, which are really powerful for these kind of prediction tasks. Now, in order to get prediction regions, so basically these blue balls that are indicated over here, we take the 1 minus delta over tth quantile of the non-conformity score that I've written down here, which is simply the prediction error that we're making. Now, it's important to note that we divide delta by t over here, and we do so to account for the fact that we would like to have prediction regions over multiple time steps. By doing so, what we show is that with a probability of 1 minus delta, we quantify prediction regions indicated here for multiple time steps. So for capital T time steps over here. Let us just illustrate this. We implemented this in Carla at a pedestrian filled intersection. So we just let pedestrians start from random initial conditions and let them walk at random speeds. We trained an LSTM from collected trajectory data, and we compute conformal prediction regions. What I'm showing here are two histograms for the 2.5 second ahead prediction and for the 4 second ahead prediction. On the x-axis, you can again see the prediction error, and on the y-axis, the frequency by which or how often we have this prediction error on a validation data set. Importantly, in green, I show the size of the prediction region, so the quantile basically. And we can see that as our mission horizon capital T or the prediction horizon capital T increases, the size of the prediction regions will increase, which is just natural. Now, what we can do next is we can use these prediction region to design an uncertainty-informed MPC. We simply use a standard MPC that minimizes a cost subject to dynamics constraint as well as input and state constraint and our safety constraint. However, what we do here is we tighten our safety constraint C that acts on the state of the robot as well as the prediction of the pedestrians. And we tighten the constraint by the Lipschitz constant of the function C times our prediction region over here. In a toy example, just to illustrate this, we have 3 pedestrians and 1 robot that navigates around them. You can see the prediction or the prediction regions in green, and you can see that they have a cone shape, which is just natural since as you predict more steps ahead, you will get more uncertainty. That's kind of natural. We evaluated, before we evaluated, just the result that we show is that if we can show, or under the assumption that the MPC is recursively feasible, we can show that we find a safe path with a probability of at least 1 minus delta. And now we evaluate this in Carla. First of all, what we did was we checked the 1 step ahead predictions, and we were guaranteed to have correct prediction regions in 99.83% of the cases. And empirically, we found that we're even a little higher, that we have 99.98%. When we run this MPC, we observed only 1 safety violation from 100 test runs, while we were guaranteed to have at most 5 violations. Okay, now I would like to move on to the last part of the talk, which is about distribution shifts. So first of all, why may we experience distribution shifts? Assume, for instance, that we have observed trajectory data at an intersection with mainly old people. Naturally, old people walk more slowly, make more stops, for instance. They may just stop in between to take a rest. However, if we have this offline trajectory data, we may not be able to use our algorithm at an intersection with kids that may behave more erratically and may simply walk faster. Right? So this is a distribution shift, a distant difference between training and test time data that we have. What we can instead do is we can use adaptive conformal prediction to build prediction regions from an online data stream. And the important thing here is that we don't need any offline trajectory data anymore. So how do we do this? We simply use ideas from online learning or adaptive control, whatever you may want to call it. And the idea is based on defining an error at the ET, which defines the empirical coverage that we had on past data. So we basically check how good our prediction regions were on the past data stream. And from there, we compare this empirical coverage with a desired coverage level delta. And we multiply this error, or the discrepancy between our desired and the empirical coverage, with a learning rate gammas. And the learning rate basically determines how fast we may be adapting to distribution shifts. And then we simply update our coverage level delta t that we use to build our quantiles, our 1 minus delta t quantiles in this case. We evaluated this on a double pendulum, a two-link pendulum with positions x, y, and z for both links. What I'm showing here on the top row is the 1 step ahead prediction error, and the bottom row is the 6 step ahead prediction error. In orange, you see the true error that we observed as we go by, and in blue, our prediction regions. For desired coverage of 90%, in this case, we had a higher coverage, empirical coverage of 99 and 98%. For the 6 step ahead prediction error, it was a bit lower, but still exceeding the 90%. We can go ahead and use these adaptive prediction regions again within an MPC. And what we then show that if the MPC is recursively feasible, we find an on average safe path. And by that, I mean that if we average over the probabilities over time that we satisfy our safety constraint, these average probabilities will be lower bounded by 1 minus delta minus a correction term that consists of delta 0, our initial guess of delta, plus our learning rate divided over the mission time t times gamma. And you can see as t goes to infinity, this term will vanish, and we will on average have safety with 1 minus delta probability. We implemented this on a drone, this MPC, to avoid a flying frisbee. So this flying frisbee here has highly nonlinear dynamics. Our drone is modeled as a second order system. And I just want to show a real quick empirical evaluation that we did. Here we have a delta selector of 0.025 and on the other column of 0.05. And we analyze the success rate, so how often we satisfy the safety constraint, and the minimum distance between the drone and the frisbee. And here is our proposed method in this column, which we compare to 2 competing methods, one using an extended Kalman filter, another one also using a type of risk tightening approach. The interesting observation here, though, is that we would like to have constraint satisfaction with 97.5%. We exceed that with 99.2%, which also the other 2 methods do. However, we're much less conservative. We have an average distance to the drone of only 3 meters, while the other methods have 14.2 and 5.3 meters, which shows that we can operate closer to performance limits. And this is an indicator for us that the other 2 competing methods were just largely overestimating the uncertainty, while we have a realistic estimate of uncertainty that lets us operate less conservatively. And the same applies for the case where we have a delta of 0.05. And by that, I would like to conclude the talk. I would like to thank my collaborators who I've listed here. I've also listed the relevant papers for part 1 and part 2. So for everyone who's interested can check out these papers, and I'm happy to answer any questions that you may have.
Thank you, Lars, for the great talk. Let's open the stage for questions. You can either raise your hand and ask directly or write in the chat, and I will read the question for you. Tassos, go ahead. You can start.
Hi, Lars. Thanks a lot
Tassos.
for the talk. Nice to see you.
Nice to see you.
I'm curious, have you thought about comparing the conformal prediction method with scenario approach?
Not with scenario approach. We compared with Gaussian processes. So we used the Gaussian process to predict the 1 step ahead prediction error in this pedestrian scenario that I showed. And we had a desired coverage of 95%. And the interesting thing, what we saw is under this Gaussian assumption, our distribution is highly non-Gaussian, by the way. We only had an empirical coverage of 67%. We didn't compare it to a scenario approach. I would assume that a scenario approach is closer to reality simply because it's also sampling based.
Yeah, it would be interesting to see. I think if it's I think this should be computationally less intense, probably.
Yeah, so yeah, I mean, I think there are a lot of statistical tools that may give you similar guarantees. I think what motivated me to go into conformal prediction, and I should have emphasized this a bit more, is the simplicity of the method. So the proof of the method is basically 8 lines, the quantilemma, and coding it down is basically 5 lines. So once you have your validation data, you can really easily implement it and use it downstream for planning and control. Now, there are several challenges we need to address, but I think for the robotics and autonomous systems community, it's a nice tool that is easy for us to understand and use downstream to address problems. Yeah.
Thanks.
Jesus, any other question? Yeah, there is one in the chat. Thanks for the great talk. Can we use control barrier function with reinforcement learning for autonomous systems that can safely and efficiently navigate uncontrolled environments and maintain control in adverse situations?
Yeah, it depends on what scenario you're looking at. So what you could, for instance, do is once you have, so I mean, it's kind of the problem with model knowledge, right? I mean, in our approach, we assume that you know the model of the system, while in reinforcement learning in general, you assume that you don't know a model. So assuming that you already have learned a control barrier function would assume that you already have a model at hand, so that then reinforcement learning wouldn't make a lot of sense, I would say. What you may be able to do is to simultaneously learn, explore the environment, learn a model, and learn a control barrier function to episodically increase and improve safety. That's what you may be able to do. But I think the problem setups here are a bit different. Like I said, in reinforcement learning, typically you assume you don't know the model, while in our framework, we assume that at least you have a model of the system.
Okay, also, let's see, I don't know if Adil is satisfied with the, but let's move to the, oh yeah, seems so, thanks. David, you have a question, go ahead.
Yes, hi Lars, I don't know if you can see
Hey,
me.
David.
Thanks for the nice
Yep.
presentation. About the conformal prediction, do you have any way to choose how many samples you need, or like sample trajectories?
Yeah, you have a bound. Let me just go back to the slide. So what's important is this equation here. So again, you take the ceiling, so you round to the nearest integer from above of k plus 1 times 1 minus delta. And what needs to hold is that this expression is smaller or equal than k, than the number of trajectories or data points that you have. If this number here is greater than k, the prediction region will be infinity, so basically useless. Yeah, so this gives you a bound on the amount of data that you need to have for choosing delta, for choosing failure probability. And you see as delta goes smaller, becomes smaller, so 1 minus delta becomes larger, approaches 1, you will need a larger k, so larger amounts of data.
I see, okay. And it goes to infinity because you put infinity in your set, or is that like one of the conditions?
Yeah, exactly. So the quantile that you have over here is over the 1 to k values and infinity as well. And you can show that once this value here exceeds k, then basically infinity will simply be the quantile.
Yeah, makes sense.
And it kind of intuitively makes sense, right? If you don't have enough data to show something, then the best bet you can do is to set the uncertainty to infinity.
Yeah, makes sense. All right, cool. Thanks.
Thank you. Any other question? Okay, Vikyat has a question. Thanks for the talk. I have a question regarding the safe bounds trajectory set. Can we include the effect of robot motion on dynamic obstacles? Predicting how ego motion can affect the behavior of other agents in the environment?
Let me just read that again. Oh, okay, that's a really good question. So this is one of the open problems, I think. The question is basically about if so far we assume that this offline trajectory set that we have is basically not affected by the motion of the robot. However, the robot may affect our pedestrians. For instance, if the car is driving too closely to the pedestrians, it may happen that the distribution, in fact, shifts. And there are certain ways of how you can include this effect. One being is you can use adaptive conformal prediction to account for this distribution shift that the action of the robot may have on pedestrians. Another way would be to use robust conformal prediction that allows to account for some amount of distribution shift. So you can quantify how much our robot can affect the dynamic obstacles. And then in the MPC, you can include additional constraints that limits the shift that the robot motion will have on the dynamic agents. This, of course, assumes that you have some model of what the effect of a robot action will have on the dynamic obstacles, if that answers the question.
Okay, yes,
But this is a really relevant question that I've started thinking about like a couple of months ago, really intensely. And I think there's a lot that needs to be addressed once you take interaction into account, how you can still obtain safety guarantees and obtain sound algorithms.
Sounds good. Any other question? I have a short question, which is, I mean, the second part of the talk, what's very interesting to me is that it seems very modular in each one of the different steps, right? For instance, you showed at some point for the predictions, you showed the trajectron, but also more basic techniques. I was wondering, does this modularity allow you to, for instance, then think about designing different components at the same time? I'm thinking, for instance, designing the perception system together with the planner and the controller, instead of, doing that sequentially. Have you thought about that?
In a way, it does, yeah. So, for instance, this box here, you can design basically together. I mean, so in a way, I mean, the model predictive controller depends on the predictor as well as the conformal prediction region. So it's kind of a downstream kind of, you shift it through, right? So what you can do is you can independently design your trajectory predictor. Of course, you would like to do as well as possible. But I don't think that you can design the MPC and the trajectory predictor without incorporating the size of the prediction regions that you may have, simply because if the prediction regions are too large, your MPC may become infeasible. What you can do, though, is what you said is really to design this perception and prediction pipeline independently. And depending on how well you do, you will get good control performance. Now, there are a lot of interesting questions how you can close this loop and not only have it sequentially. One, for instance, being is, can you use the information from the prediction regions that we have here? So basically, it gives you information about the quality of the predictor to retrain the trajectory predictor. So can you find counter examples from here to improve your predictor, for instance, for corner cases, right? Another question that I partially alluded to before is already, can you close the loop from the controller to the trajectory predictor or to the pedestrians even, right? Because again, the action that we may have over here may affect the distribution and the behavior of the pedestrian, right? How we can account for that. And this is kind of, to me, a bit of an open problem right now. Like I said, I mean, you can use adaptive conformal prediction. The guarantees there are a bit weaker, though, that you obtain, or you can use ideas from robust conformal prediction. Basically, it gives you prediction region under some level of distribution shift. And you can then basically anchorage the MPC by an additional constraint to not induce a distribution shift that is larger than this desired level. And by that, you kind of close the loop.
Yeah, very interesting. Thank you. Let's see, is there any closing question? I don't see anything else in the chat, but maybe there's some final question from the audience. Doesn't look so. Well, I think you provided some contact also if people want to reach out for deeper questions. Thank you again very much, Lars, for waking up early to give this talk and also for the very interesting insights.
Yeah, thank you for the
Yeah.
invitation. Yeah, thanks for doing this despite having your job interview, basically. So really appreciate it.
No worries, multitasking is the way. And I will follow up with the video once this is edited, and I wish you all the best for the next steps.
Thank you so much. Yeah, have a good rest of the day, everyone.
All right.